everyone. So the bubbles in the air is very fascinating to see, but when it comes to the material, they are considered as defects, and everyone wants to get rid of them because they weakens the material. Now, we wanted to use this weakness, the strength in this kind of sensor development, which is called supple side. So this is based on the principles of the haptic sensor developed in previously by the Adelson group. So basically it includes LEDs, camera and collimator, mirror, one acrylic body to take the light forward, and a contact body, and the reflective layer and protective layers. And the marker layer, for if you apply some force, the marker movements can be observed through the light propagation through the medium. And this is the some literatures which have been done from 2017 to 2023 by the Adelson group. So these are called gel set and its variants. Similar work is done by the Catherine groups, which basically changes the intensity of the light when you apply the force on the elastomer. So the elastomer is this is working. Yeah, so this is the elastomer, and here if you apply any force, the intensity of the light will change, which can be captured by the camera. So currently we have developed this one, which is called bubble supple side, which incorporates a single bubble inside a elastomer. Now it can enable to sense 3D sensing. Though, if you apply forces from the radially or compressive or shear force, this can sense the deformations. And another thing the bubbles does is that because it weakens the material, it can sense lower forces. So, and you can include similarly a number of bubbles, then that will be called as bubble side, and it can be curved also. So this is the configuration that we are talking about. And now basically why bubbles? Now if you do a force deflection curve with and without bubbles, so you can see here for a small value of force, the deformation is higher, and we have put here different hyperelastic models to basically Newhookian and Moni-Rivlin and Ogden models. So to match the characteristic and the coefficients, the modulus coefficients we found from the optimization. So if you see the error from the experimental value, so the Ogden and your models are performing better. So you will take these coefficients for our further analysis. Now, similarly, coming to the cyclic loading also, so it observed with bubbles, it has a lesser hysteresis because the pressure inside the bubble helps the material to come back. So that also is observed in this kind of a cyclic loading. So how we fabricate, basically we mix two elastomers and allow it to degas completely. For a single bubble application, we'll wait for the elastomer till it reaches certain amount of viscosity, so that when you incorporate the bubble inside, it will not come out of the surface. So that is around 3000 to 5000 centipoise second. When the viscosity reaches, after about 20 minutes, we can inject one bubble inside the elastomer so that it can be stabilized inside that, which is shown in the figure. So the algorithm can be anything. Now we can follow the contour change inside the bubble or the optical flow when you apply the force. So the displacement vector during the optical flow can be a measurement of the application of force. Now this is a calibration and the simulation setup where we are indenting the single bubble here. So this is the bubble which is given here, and this is the indenter. Similar, it is in the simulation model is shown, and the parameters of elastic model is taken from the optimization that is previously we discussed. And this is a application setup where we placed it on the radial artery to get the force distribution on the artery. And the light ray, how it transmitted is by the principle of transmittance here. So light passes through the bubble and it gets internally reflected also. So that's how we'll get the boundary of the bubble there. So in simulation, we are trying to see the depth. If you place the bubble at different depths, how the response is. So the perimeter change is shown in this figure. So when you apply force from 0 to 5 Newton with the different clearance of the bubble from the surface, how the range behaves. Now for different when the bubble is placed at a greater depth, then you need to apply more force to sense the deformation. So it basically increases the range with the depth. If it is at the surface, now it can sense very low force. Now coming to the calibration results, so we have given this step input at steps of 0.5 mm displacements of the indenter, because you can control the displacement very accurately, and the force response is shown over here. So you can see it's a kind of a second order response, and the hysteresis also is shown here for different displacement of the indenter. Now with higher displacements, the hysteresis, you can see the area of the hysteresis is increasing, and the drift is shown. There is a murmur during the steady state. You can see some sort of drifting happening. So that drift also increases around 15 to 17 millinewtons with higher depth of indentation. The drift is also is relatively greater. Coming to this, when you see this this as input, the deformation as input and the force as output, and you do the system analysis, you can see at higher depth the system behaves like a higher indentation. The system behaves like low pass filter, so it behaves like a first order system response. But for other depths, it is having a second order response, and slowly the corner frequency is shifting towards left with the depth. So it shows that the low frequencies are getting identifiable than the high frequency over here. So the way bubble at the surface can be very good application for the getting the high frequency informations than at a higher depth. So in the static response, we have applied, we have deforming the gel from 0 to 0.5 Newton in steps of 0.1 Newton. So the output response of the force you can see over here, which is repeatedly has done for 4 to 5 times, and the aggregate result is plotted here. So with the increase of the force, this is the you can fit a linear curve to get its sensitivity, which is around 25 millinewton of resolution, and the sensitivity comes around 20 millinewton. So this is a kind of application which when you placed on the radial artery, the you can see the video there. So it's kind of an analog twin of your heartbeat, so which is transformed into the bubble motion. And if you plot and take its Fourier transform, the displacement vector from the optical flow, it comes around 1.3, which is pretty much the heart rate. And coming to this load applications, if you apply a normal load, so this is going to deform like this. So I'm just applying through my fingertip, and this for the radial load, and this for the shearing. The calibration is only done for the compressive load alone. So in a conclusion, what you can say is that as the depth of the indentation goes beyond 2 mm, the bubble behave as a first order response, and from the simulation we observed, and at lower depth of indentation the high frequency components are evident, and vice versa from the border plot. The sensitivity we observed is 20 millinewton, the resolution is around 25 millinewton, the drift is around 17 millinewton, the range can go maximum 2.5 Newton, after which it's kind of saturates. This is done for the bubble size of 1.94 mm. And if you have a good camera with higher resolution, then it can also sense force in order of 5 millinewtons or so. So, and yeah, with the depth, the sensitivity decreases with the depth of the bubble, and the range can be maximized with the depth. So the future work includes mapping these changes with respect to the contour of the bubble, and how the gel behaves when you have plural bubbles in the matrix. So these are some reference, and so I need to thank the Minister of Education in India and IIT Madras for the research that I'm doing now.